All right, should we start? Okay, my clock says 2 o'clock. So, in my humble opinion, this day right here, hardest day of the semester. And spring break, all one big tease, as far as I see it. So, I want to know who went the far. Oh wait, hey, we can make an algorithm for this. Okay, let's do this. I want to know who traveled the farthest, but don't solve the problem yet. But my whole goal is I want to know who traveled the farthest within the last 10 days, okay? And let's see, how should we do this? I don't know. Yeah. 105 style? Oh. Stand up if you traveled farther than 50 miles this spring break. Everybody has to stand up, right? Or not. If you traveled over 50 miles. Oh, this is good. This is like, hey guys. So I want to give you a geeky picture of this, okay? So in third grade, my turn. In third grade, you learned about presenting data in bar charts. The way I see this little drill that we're about to do, and your presence here, is like a bar chart through time. We're effectively seeing a cumulative value for each of the distance increments that I'm about to see. So what I look at you right now and I say, okay, look, about half the class traveled farther than 50 miles over spring break. Now, I'm going to ask you to sit down if you did not travel one way to a place more than 200 miles away. So if you went to Chicago, you sit down. If that was your distance, okay? If you did not travel more than 200 miles, sit down, okay? If you did not travel more than 1,000 miles, sit down. Oh, wait, that's too far, right? Stand back up. 500 miles. One way. These are all one-way questions. If you did not travel more than 500 miles, sit down. So everybody standing now traveled more than 500 miles. Okay? So where did you go? Where's that? Mexico? You went to Cancun? Oh, okay, you win. All right. Sit down if you did not travel more than 1,000 miles. So the East Coast, East Coast is within 1,000 miles, right? About? Okay. All right, here we go with 2,000 miles. Anybody travel farther than 2,000 miles? One direction. Where'd you go, Mark?
I'm setting you on the technicality. It's because the solar system right now is moving in.
Oh, boo. Nice. Okay, where'd you go? So did I. Are you from Vancouver? Okay, all right. Where did you go? Beijing. Okay, did anybody go farther than Beijing? Okay, you win. Yay. All right, where'd you go? Moore Park, is that Bay Area? Southern California, okay. That's like 2,289 miles from here. Have I done that road or not? Oh, okay, you win. 2048. Where'd you go? England. You went to England? Oh, maybe you win. Yeah, that's more fun than Beijing. Well, yeah, but Beijing, yeah, all right, fine. One ocean either way. Okay, everybody sit down if you did not go More than 10,000 miles over break. Okay, everybody's saying that. Sit down, Mark. Sit down if your name is Mark. All right. That's okay, Mark. All right. Oh. So I hate to break it to you, but we were talking about binary search trees. We were talking about a special kind of binary search tree. Let's see. Almost there, sorry. Yeah? Oh, yeah. You guys, lecture helper is alive. So that is lecturehelper.cs.illinois.edu if you'd like to ask questions. Yep, it still works. We think it still works. We haven't used it since March 6th, apparently. All right, here we go. All right, I want to know, first of all, I want to know if that is a binary search tree. This tree right here, is this a binary search tree? Take your time checking. Yes? It's a binary search tree? Yes, I agree completely. Somebody prescribe for me the algorithm you use to check. What would be a reasonable algorithm for checking to see if this was a binary search tree? And looking at the screen, oh, your algorithm should work for trees much, much, much larger than this one. So what's a reasonable algorithm for checking to see whether this is a binary search tree? Yeah? Very good. Do an in-order traversal and check and see if it's in order. That's right, increasing. See if the keys found in each of the nodes are increasing as you go. You can either do it as you go, or you can dump them all out, or you can keep track of the previous one that you outputted and check to see that you're incrementing every time. Lots of different ways of actually implementing the algorithm that he suggested. Here's another question. What is the running time of the algorithm? And what I want you to do is answer that by whispering it to the person sitting next to you. Whispering the answer to what is the running time to check of the algorithm that checks to see whether that's a binary search tree. Running time of BST check. Okay. You're supposed to whisper it to the person sitting next to you. That's okay. You just have a loud whisper. All right. So now what I want you to do is shake your head like this if you gave an answer that disagreed with the person sitting next to you. And all I'm doing is looking around to see how many people are shaking their head. Okay. All right. Whoa. Who is shaking their head over here? Did you tell somebody? Ah, okay. All right. So the algorithm is traversal based. Anytime anybody tells you an algorithm that is traversal based, your initial reaction should be that it's a big O of N algorithm, or AKA linear time algorithm. Your gut, your instinct should be to say that it's a linear time algorithm, unless you have some reason to believe that it's not. So, for example, if instead of just basically printing out or looking at each of the values in the traversal of this, you did more work at each node, if you did more work at each node, then it's possible the running time would not be linear. But if you do a constant amount of work at each node during a traversal, then your algorithm will be big O of N, or proportional to the size of the data. Okay, that was meant to summarize about 3 weeks worth of stuff. Okay? Now I have another question. This is getting back at where we were. I want to know if this is a balanced binary search tree. Is this an AVL tree? And if it is not, then what I'd like you to do is take your fingers and put a finger on each of the nodes that's out of balance, that is the root of an unbalanced tree. Okay, so I want you to take your fingers on your piece of paper, not on my piece of paper, and put your finger on every node that is not the root of a balanced binary search tree or an AVL tree. Okay? How many fingers did you need? Somebody raise their hand and talk to me. Be willing to talk. Nothing ventured, nothing gained. Yes? You used 2 fingers? Where? He used 2 fingers. He found 2 nodes that were the roots of unbalanced binary search trees. Can you show me where you put those? Uh-oh.
Oh, that's not good.
There. Show me where you put your... Wait a second. All right, so let's do the easy one first. What's wrong with the node or the subtree rooted at 5? What's wrong with the subtree rooted at 5? How is it not balanced? Gabe, you want to tell me? Yeah, very good. Perfectly stated. The difference in heights between its children, its left and right subtrees, is greater than 1. In this case, the height of the left subtree minus the height, the height of the right subtree minus the height of the left subtree is -2, right? Do you all see that? The most important point is that the absolute difference is 2. Okay, any question about the fact that 5 is not the root of a balanced binary search tree? Any question about that? You totally buy it? Okay. He circled 8. The heck? Is he right or is he wrong? Am I setting him up here? Because look, the height of 8's left subtree is 3, and the height of its right subtree is 2. The difference is 1, so looks balanced to me. Yeah? Right, remember, height balance is a recursive definition, right? So that's only a height balance tree if the difference in the heights of the subtrees is no bigger than absolute value. Absolute value of the difference is no bigger than 1, and the left and right subtrees are height balance trees. So, good job. 2 fingers was exactly what you needed. And any questions? Are there any questions? So thank you. Perfect. Any questions about it? Yeah? It's right minus left, technically. It doesn't matter. So you know what? I screwed up, right? Early on, when I was talking about height balance, it was height of t something minus the other. It doesn't really matter as long as you are consistent. For the purposes of this class and the example code that I'm writing, it's going to be right minus left. I think in my original definition, I even had left minus right. But for the purposes of, for the, oh. Okay, good. That's good. All right, so for the purposes of our discussion today, certainly it's going to be right minus left, okay? if you see a definition that's left minus right, that's okay too, as long as it's consistently applied. All right, any questions so far? Okay, so here's what I want to do next. I want to play with these things just a little bit. See if I can find it somewhere. I had it open. I had it open in, here we go. Okay. First of all, is this, yeah, I'm punting. Oh, it went. Is that a height balance binary search tree, aka an AVL tree? What's your biggest clue? At the top there, see how AVL tree is highlighted? Constant time, check. Oh, it also says the tree is now balanced. Another constant time check. All right, so here's what we're going to do. I want you to tell me a key that I can enter. Actually, think in your brain. Don't say it out loud yet. Think of a key that you can enter into this binary search tree that would induce some kind of rotation. That is, that would induce some kind of reformatting of the tree in such a way that balance is maintained. Okay, so did you think of a key? Everybody think of a key that if you inserted it would induce some kind of rotation. Okay, everybody got one? All right, anybody want to volunteer? Yeah? 71, all right. Whoa, what's going to happen if we insert 71? I'm going to do this like this. This one wants to insert 51. Oh, that would be fun too. But we'll do 71. Okay. Here's what we're looking for. Here's what we're looking for. We're going to, the algorithm will find the right place to insert 71 and then maintain balance on the way up the tree as the recursive inserts are completed, okay? I'm going to talk aloud a little bit in that process. So here we go. Are you ready? I don't know where 71 goes for sure, but it goes in 67's right, 70's right, 74's left, 72's left, and we get the new node. We won't be able to see it. Okay. Oh. All right, I should be using that instead of mine. And now we'll check for balance. 72's not out of balance. 74 isn't. 71 goes, uh-oh, too long. I think I'll do a rotation. Around 70, was around 70, okay? Now, I can't go backwards. All right. I want another key that can, any question about that? Okay, I want another key that will induce some kind of rotation. Think it to yourself for a second. Induce some kind of rotation. Yeah, Neil? 66. Okay, so we're going to insert 66. Now, my question to you, to all of you, is by inserting 66, am I going to create some kind of left rotation or some kind of right rotation? So take a look at where 66 is going to go. Oh, no, I disagree completely. How about 51? Yeah, so do you see where 66 goes? It goes over here, and that won't change any balances, okay? All right, so let's look at 51. Let's look at 51. Where does 51 go? 30's right child, right? If you put a node at 30's right child, walk up the tree. Where's the first time you hit an imbalance? Help me figure out where's the first time you hit an imbalance. walking up the tree. Where is it? So I'm going to insert 51 right here, right? Essentially right above my hand. 30's right child. Okay, is 30 out of balance? No. Is 29? Is 53? No, it's not, right? Because the height of the left is 2, the height of the right is 1. That's a difference of 1, that's fine. How about 67? It is, right? Oh, no, it's not. That won't do it as rotation. Yeah? How about 90? Oh, maybe that's the only one we could insert that would induce a rotation. Oh, 55 would. Okay, I see now. I'm going to do 55 because it's the same kind of thing. But I can see it better. All right, sorry. All right, where's 55 going to go? It's going to go right here, right? Now, my question for you is that going to be fixed by a left kind of rotation or a right kind of rotation? Do you think? Yeah? Some kind of right rotation, that's right, because 64 is going to be out of balance, and we're making it long on 64's left. So we're basically going to take this tree and rotate it up. So let's watch that happen. Let's watch that happen. Insert recursively, insert recursively, insert recursively, insert recursively. 55. I don't know why it's not showing up. Check for balance, out of balance. So swap the pointers around and then continue your merry way up the tree. Okay, happy? All right. That was a right rotation. Okay, I don't like this tree. It's almost too balanced. No, because then it would be perfect, and then it's really hard. Then it's a long time till we make one. Here, I'm going to reload this and see if there's anything interesting we can ask. Is that an AVL tree? No, notice it's ugly, right? That's an ugly tree. How about that one? Well, yeah, it is. Constant time check. But also, the difference of all the heights is never any more than 1. Okay, I want a value that when inserted, and I'm not going to be able to do this, but I want a value that when inserted would induce a double right rotation. So some kind of right rotation, and my big hint is I actually can't do this because this thing takes integer values. So I want some kind of, oh no, God, I suck. We have to do a left rotation first. We can't. I don't like this tree. Let me reload again. Why? Why do we always get the same one? Create. Random. All right, I like that one better. All right. Tell me something that will cause a left rotation, a double left rotation. Double left. Double left rotation. Maybe we haven't talked about this enough. Yeah, okay. I'm going to use my cursor here. If I do an insertion right here, so 98 or 99, 72 is going to be out of balance. It's easy because this is a little stick, right? And a rotation will change the stick into a mountain. What is not handled so gracefully is if I do an insertion here. Okay, if I do an insertion in 97's left child, 72 is still out of balance, but a simple left rotation won't help anything. So what we do instead is we do first a right rotation around 97 to create the stick that we like so much, and then a left rotation around 72. So let me show you. We'll talk about this in a little bit more detail in a minute. But I'm going to go ahead and insert 78. Are you ready? Make sure you see where that goes. So we're inserting 78 right there. Oh, 97's in balance, 72 is not, so there were 2 rotations there. Okay? Any question about it? Notice that by fixing the balance on this right side locally, the balance at 56, which was temporarily bad, has also been fixed. Okay, I think enough playing around here. This application is going to be useful to you as you develop your own understanding of this, but I want to go back and get technical about how we figure out concretely which of these rotations we need to do. I'm going to go back to here. All right. I'm only going to talk about left rotations and double left rotations. So left rotations of 2 different kinds. I'm saving you the boredom of having to go through the analogous conversation with right rotation. So everything I say has a symmetric operation for right rotations. Okay, so let's do this. Here's the setup. What we're going to say is that this tree has an imbalance and we did an insertion down here. Okay, so our goal was to insert something into the tree, and that insertion happened in this subtree. Okay? Furthermore, to reemphasize, we detected an imbalance. So the balance factor here is 2. That's the setup. Now the question is, what kind of rotation will fix this? The imbalance is detected here, which means the balance factor is 2. The insertion happened down here, and I'll tell you right this minute that a left rotation is the thing that will fix it. The justification is, just like we saw right at first, that these 3 nodes are in a line. They're like a stick, and the rotation, the operation that we talked about 2 weeks ago, that rotation is what changes it into a mountain. So this tree will change into something still with 3 blue little dots, okay, where this is 1, 2, 3. It'll be 1, 2, 3. And these triangles, T1, subtree 2, subtree 3, and subtree 4, they still go in order across the bottom, okay? So that's the rotation itself. That's a left rotation. Okay, now I know, you and I know by looking at this picture that I could have diagnosed the fact that something was inserted here by noting the difference in the keys at this point. So while we were doing an insert, we went right here. Okay? We could use that to determine that we needed a left rotation. But I'm going to choose a different metric here because I'm going to choose a metric that we can use in removal as well. And that metric that I'm going to choose is the height balance at this node. Okay? So I've already used height balance here to diagnose some kind of left. And now I want to use the height balance at this node. Here, I'll put it in another color so you can see it. The height balance at this node to determine the fact that it's going to be a single left rotation. That height balance is 1. or that balance factor, that's the difference between heights, is 1. Okay? Now, a very brief explanation about why it's 1. I'm not good at this explanation. I'll tell you that right now. Okay? We'll see how it goes. We would not be doing anything at all if we did an insert here and no heights were changed, right? Because if no heights were changed, then we wouldn't discover an imbalance up the tree, okay? So heights have been changed, okay? Furthermore, we've changed heights. We've inserted into the green underlined node's right subtree. So we must have increased its balance factor. Now that increase can go from -1 to 0 or 0 to -1, because remember that one's not out of balance. If it went from -1 to 0, then it would have been that this were the longer tree to begin with. T2 was longer, and we inserted in here to create a balanced tree, which would not have affected the balance factor above. Okay, so it has to be that when we change heights here, we change the balance factor in the green underlined spot to 1. Couldn't have changed it to 0 because that wouldn't have resulted in an imbalance one level up. So our strategy for diagnosing a straight single left rotation is going to be eke an imbalance of 2. Furthermore, a balance factor in the right subtree of 1. So a difference in heights of 1. So a 2 and a 1. Okay, and that'll give us a left rotation. Similarly, the discussion in this picture is the following. Again, the imbalance is detected here. Oops. So its balance factor is 2. If it were -2, we'd be talking about rights instead of lefts. So its balance factor is 2, and we inserted here. Okay, those are the givens. Now again, we could detect that by looking at the magnitude of the keys, but instead I want to look at the structure of the tree itself. We detect that this height has changed by noting that the balance factor, the balance got longer on the left, which means it gets more negative, right? It's right minus left, so left gets more negative. And with an argument that's exactly like the one before, this can't have moved from 1 down to 0. It had to have moved from 0 down to -1. So, if an insertion was in subtrees T2 or T3, and if an imbalance is detected at T, then a double rotation, a right-left rotation about T, rebalances the tree. Remember, that's right around this node and left around this node. Okay? Gauge that by noting that the balance factor still at T right is -1. Okay. That's all I got. I think if we pull together all the pieces that we've talked about, we've got ourselves an algorithm. I hate this slide. I hate this slide and I hate the next slide, both of them. Here's why I hate this slide. My plan for this slide is to unroll a recurrence, a recursion, a recursive function. I hate unrolling recursive functions, okay? Because it feels like I'm denying the magic of recursion by doing so. But I want to do it so as to illustrate the post-order processing of the balance checks, okay? So here we go. I'm going to insert into this entire tree this value, Okay, I don't care what it is. I'm just going to insert something that goes right here. Here's my pseudocode for the function insert. This insert right here is a recursive call. The proper place means, what does the parameter look like? So this is the recursive call to insert in the correct subtree. All right, so I call insert on the whole thing. The first thing that happens is we insert at the proper place, which has to be this subtree. What does that call to insert do? Why, it calls insert in this subtree. What does that insert do? Well, this is why I don't like unrolling it. It calls insert into this subtree. What does that one do? Calls insert into this subtree. What does that one do? It calls insert into this subtree. Finally, we're at the base case. What does the base case do? It creates a new node, updating its root, right? Updating where it's hooked in. And then it does the following, okay? Check for imbalance, rotate if necessary, and update the height, and pass control back to the calling function. So after we create this node and update its height, we pass control back to the blue triangle. What does the blue triangle do? That's this one. Now we're here. We're basically here. We need to check for imbalance. Is there an imbalance? No. So we don't have to rotate. Do we have to update the height? Do we have to update the height of this guy? Yes. It used to have height 0. Now it's the root of a subtree whose height is 1. So we do update the height. And then we pass control back to the calling function, which is the red one. Wait. Yes. Okay. The red one. And now we're sitting right here with this as the root. Is there an imbalance? No. Do we have to update the height? Yes. Its height gets updated and we pass control back to the green. Now we're sitting here. Is there an imbalance? No. Right? No. No imbalance. We update the height and we pass control back to here. Now things get interesting, right? Because now there's an imbalance. But we know all the information that we need. We know the height of this subtree. We know the height of that subtree. From that information, we can get, and furthermore, we know that we had a recursive call here. So we can get all the heights that we need to do the evaluation. Now, my question for you is, what kind of rotation is going to fix this? What kind of rotation will fix this? Here's the imbalance. The imbalance is here. Yeah? Yeah, very good. It's a left-right rotation because we inserted in the nodes left, right. We inserted around the corner. Okay, so a double rotation will work. So this is going to be a left followed by a right rotation. Okay, any question about that? And then we update the heights. Pass control back to here. After a rotation, there will never be another rotation going up the tree on insert. But it doesn't hurt to always check. You'll always check balance anyway. All right, any question about that? Okay, you're good? All right, I hate this slide too. You can tell me why. I like that we're flipping the page though. That's a good sign. All right, so let's take a look at this. This is the code for insert, okay? I know that because it says insert right there. Let's look at the parameters. Here is the key to insert. And, oh, Yes, and here is the root of current subtree. If I were commenting this code, what would I put as the comment for that line, the if line? What would my comment be there? Good. I would say this is the base case of the recursive insert. Okay? Got one more question for you. What's that? What's that 0? Good. Look, I snuck something in on you. I sneaked it. A tree node? A tree node contains a height. This 0 is simply the height of a single node, right? The height of the new node. Any question about it? Okay, now things get complex. That's the base case. That's always easy. Now things get complex. Here's the general case. These two lines together and these two lines together are the insert at the proper place, right? It's the conditional that decides where that proper place is, and then the insert statement is the recursive call. So this part is the insert at proper place. Okay, any question about that? So if your key is less than the if your key is less than the root, you go to the left. Otherwise, if it's greater than the root, you go to the right, right? You've known this for a really long time now. All right, now I computed two things that I know will be important to me. I'm going to need the balance of the current subtree so that I can detect whether there's an imbalance. And moreover, I know that I'm going to need the balance of the subtree. Now, I look at that and I go, oh boy, I'm dereferencing something twice. How do I know that T left isn't null? How do I know that T left isn't null in that line of code with the arrow up here, the one after? How do I know that T left is not null? That dereferencing T left is okay? How do I know? Yeah? Excellent. That's right. I just inserted something there, right? So I know it's not null. Phew. Otherwise, I'd have to be careful, but I don't. All right, so it's perfectly safe for me to check left balance as well. Okay, now the rest of it is just exactly what we saw on the previous page, 2 pages ago. All right, if the balance is -2 and the left balance is -1, what kind of rotation will fix this? Tell me the next letter that I'm going to write. -2 means it's longer on the left. So what kind of rotation will fix that? Right, so my next letter is an R. Okay? Otherwise, I'm going to do a left-right. Left-right double. Okay? So the fact that it's -2 means some kind of right will fix it. Okay? Any question? Now, I'll bet you that you can fill in those blanks without thinking here. Shall we race? The last 2 blanks here, should we race and fill them in? Your mark, get set, go. Done. Everything about this code is symmetric to everything you see up there. That's why I hate this code, right? It's exactly the same code. Now, the problem with it is that there are a couple different ways of solving it. you could like twist the tree around in your mind. You could parameterize whether you're going left or right and, you know, fill in the blanks. But really, the simplest code you can write there that I could think of writing was this. Okay, so I just replicated the code, even though it's ugly. All right, so what I would do, though, is most likely pull all of this into a helper, and similarly, all of this into a different helper. Okay, just because it makes the code cleaner. All right, and then finally, the very last thing is update the heights. Okay, just like we saw in the pseudocode. Any question about all of this? I have a question for you. Yeah, what's the running time? What's the running time? I don't know for sure what the running time is, but I know that it is proportional to what measure of the tree? Number of nodes or height? Which one? The height of the tree. That's right. So if we can argue that we're bounding the height of the tree, then we're arguing about this algorithm. Okay, but that's a little bit of foreshadowing. We're not quite there yet. All right, any questions about this code or what it does or how it works? You're going to be implementing it. You're going to be actually typing it out and making sure I don't have any bugs in the lab, I believe, this week. We're not done. No, no, no. There is a node in this tree that is very interesting to remove. Actually, a couple of them. There are a few nodes in this tree that are quite interesting to remove. You see one? Anybody want to suggest one they think might be interesting to remove? You guys, like, one of the two of you every single time. Somebody else. Sorry. We've got corners. Here. Which of these would you like me to remove?
7.
7. Okay, what happens when I remove 7? What happens when I remove 7? Yeah? I lose balance at 5, and what rotation fixes it? A right rotation around 5. That's right. Okay, fine. There's something else incredibly interesting. If we don't remove 7, especially, 8, no, that's not particularly interesting. That's like removing 7, right? Because 7 would go up. What else would be interesting? 6 is not interesting. 10. Who said 10? Yeah, all right. Think through your mind. What happens if I remove 10? 9 comes up, right? So let's do that. Let's just do it. It's too much to talk about. All right. I want to remove 10. The first thing we do in a binary search tree to child remove is we take the in-order predecessor and swap it up. So there's 9, and all of this is now gone. Where's my white pen? Okay? Not only that, it's out of balance, right? What kind of rotation fixes it? What kind of rotation fixes the imbalance here? It's some kind of left rotation. What kind? A right followed by left rotation. So we're going to do a right rotation here and a left rotation here. What does the tree look like afterward? I'm going to do this in red. We've got 11 in the root. 9 gets its old place back. And 12 ended up not going anywhere. Okay, so now this is gone. Are we done? Why not? Yeah, look, 8's now out of balance. Look at this. We shortened this right here. And so now, we fixed this subtree. But now there's an imbalance at 8. What kind of rotation will fix that? Yeah, a right rotation about 8. That's right, because here it's longer on the left. That's right. Okay, but guess what? This 8 right here, it's just a subtree of some other tree. I didn't tell you this, but this is just a subtree of this tree. And now this one's out of balance because we shortened the right. And that one's just a subtree of some bigger tree, which is now out of balance because we shortened it on one of its sides. So, for a removal, you may have to rotate at every level of the tree in the post-processing of your recursive call, okay? You will be, I believe you're writing recursive remove, AVL tree remove in your lab. So, bye. Yeah?
So when we talk about left, right, rotate, do we need